Hello everyone, let's take a look at our next problem. 3 points A, B, and C all lie on the parabola y equals x squared. The point B is the origin. A and C are two other points on the curve. A is somewhere to the left of the origin and C is somewhere to the right of the origin. And we need to find the points A and C such that the triangle formed by A, B, and C is an equilateral triangle. Okay, so my first thoughts are obviously, we have a lot of information on exactly where the points A and C lie, a very strong restriction. They're on the parabola. And I'm now thinking that we're just going to need to write down some distances between the points A, B, and C in terms of, everything is going to be determined by the x-coordinate of the point A and the x-coordinate of the point C. So there's really only two variables here. And in fact, if it's an equilateral triangle, the x-coordinates of A and C will be equal to each other, but opposite sign. And so it's really just a one variable problem, and we're going to want to write down the distances of everything in terms of that one variable. So a sketch of what's going on here. First thing we're going to sketch is the parabola. This is not going to be to scale, but that's okay. Just throw down a few points here to sketch through. So we're going to look something like this. This is the point B, the origin. The point A is to the left of the origin. We'll just call that arbitrarily the point A. And the point C is to the right of the origin. And because we need an equilateral triangle, there's no harm in making it so that point C is just a reflection of point A through the y-axis. So this will be point C here. And what I'll do is the variable x will represent the horizontal coordinate of the point C. Okay, so the point C is going to be equal to x squared, and the point A is going to be equal to negative x squared. And the triangle ABC is supposed to be an equilateral triangle. Now, by construction, the length of AB and the length of BC are going to be the same. So the only thing we're really concerned with is making sure that the length AC is the same as the length AB. Okay? So the length AC, well, this is clearly just 2x. And the length AB, this is going to be x squared plus x to the 4 under a square root, right? And what we want is to choose x so that AC is equal to AB. I don't like square root signs, so in fact I'm going to square both sides and see what happens. So this says that 4x squared is equal to x squared plus x to the 4. And we have then 0 is equal to x to the 4 minus 3x squared. We clearly don't want x to be 0, because then A, B, and C will all lie at the origin. So we're going to cancel an x squared from both sides. This gives us x squared minus 3. And so x is going to be the square root of 3. We take the positive square root here. But of course, the negative square root is just going to interchange the roles of A and C. Okay. So this means that the point A is at negative root 3, 3. C is at the point root 3, 3. And B is, of course, still at the origin. And we can compute the numerical values now of these distances. AB is going to be square root of 3 plus 9, which is the square root of 12. BC is, the way we constructed this is going to be the same. It's also going to be the square root of 12. But just to check that we have things correct, let's compute the length of AC. The length of AC is going to be 2 times the square root of 3, which in fact is the square root of 12. Okay, so nice little problem. Recognizing that this problem, which looks like it has more degrees of freedom or more variables than necessary, really just reduces down to a single uncertain quantity, was probably the key in solving this one for me. Thanks for watching.